Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 4 of module 11. In lecture 4, we are going to cover the concepts such as the frequency magnitude relations. We will see some examples and its limitations, and then we will also talk about the magnitude invariance relations, and then finally we will have the summary of today's lecture. As far as the recap of previous lecture is concerned, we studied about the relationships between the slip in an earthquake, its fault dimensions, and its seismic movement is closely tied to the magnitude of the stress released by the earthquake or stress drop. The best constraint quantity is the seismic movement. So we estimate the average slip, that is represented by d vector or d bar, from the seismic moment as C m naught by mu L square. So C is the factor depending upon the fault shape. The stress drop is given as delta sigma is equal to C m naught by L cube, that is further equal to C m naught by S to the power 3 by 2, where S is the area of the fault. So if you are considering a square fault, then it will be this L cube may be changed to S to the power 3 by 2. So the stress drop on a circular fault with a radius r can be written as delta sigma, that is equal to 7 by 16 m naught by r cube. Stress drop on strike slip on a rectangular fault with length L and width W yields delta sigma is equal to 2 by pi m naught by omega square L. The stress drop on dip slip on a rectangular fault is given as delta sigma, that is equal to 4 lambda plus mu m naught by p pi lambda plus 2 mu by omega square L. If it is a Poisson solid, then lambda is equal to mu. Then in that case, this will be turning as 4 into, let's suppose, 2 mu m naught divided by pi in bracket 3 mu omega square L. So mu will cancel out and you will be having 8 m naught by pi 3 pi omega square L. Small differences in time function duration correspond to large differences in stress drop even for an assumed rupture velocity and fault geometry. Stress drop both characterizes earthquake source spectra and gives insight into the physics of the faulting. The ratio of the slip to the fault length is constant, indicates that strain released in earthquakes is roughly constant at about strain in the normal x direction is equal to d by L, and that will be further equal to delta sigma by mu, that is of the order of 10 to the power minus 4. Now let's start with the frequency magnitude relation for the today's lecture. And the number of earthquakes that occur yearly around the world varies with magnitude, with successively smaller earthquakes being more common. So if you look at the number of earthquakes that are distributed all over the world, then you will find that the smaller earthquakes are more common and larger earthquakes are being rare. But it has also been noticed that the cumulative amount of energy that is released within a particular period of time due to the smaller earthquakes is mostly lesser than the earthquake's energy which is having the larger magnitude. This observation says that the energy or the stress released or the movement released during the happening of the smaller earthquakes is not that significant, that is comparable to the larger earthquakes. So larger earthquakes releases more movement than the smaller earthquakes combined. So this observation was quantified by Gutenberg and Richter in 1940s via the logarithmic earthquake frequency magnitude relation, that is log n is equal to A1 plus Bm, and n is the number of earthquakes with magnitude greater than or equal to m occurring in a given time. So here you can see this relationship is very important, and it's also famously known as the frequency magnitude relation or Richter Gutenberg recurrence relationship, in which n is the number of earthquakes greater than m magnitude and a and b are the constant, and the distribution is described by a linear relation. So if you will make a graph between m and n log of n, then it will come out to be a straight line, and that we will see just in a while. And it turns out that although the a1 is the intercept, and that depends on the number of earthquakes in it in the time and region sampled, the slope b is generally about 1. So this constant a1 is basically the intercept here on the y-axis, and b basically is the slope of this linear relationship, and that is considered to be generally around 1, although it may vary from zero 0.6 to maybe 1.1 or more. So when you have higher value of b, or the higher value of the slope, which means that the stress in the region is smaller, and if you have the lower value of b, that means the stress in the region is higher, and a depends on the number of earthquakes in the time. So there is an approximately tenfold increase in the number of earthquakes for successively smaller magnitudes. So which means that if you compare the earthquakes of let's suppose a number of earthquakes for magnitude 3, let's suppose it is around 1000, then or maybe 10,000, then the number of earthquakes for the 4 magnitude will be around approximately 10 times lesser, that means 1000. Similarly, for 5 magnitude, it may be around 100, and blah blah blah. Likewise, for 7 magnitude, may be 0.1. So, this says that there is an approximately tenfold increase in the number of earthquakes for successively smaller magnitude. So, this is just an example given here. Annually around the world, there are about one surface wave magnitude 8 earthquake, and around 10 times the 7 magnitude events, around 100 times the 6 magnitude events, and so forth. And you can look at in here, you can see the b value is around 1 here, and the squares are representing the cumulative values of the earthquakes, and the triangles are representing the incremental values, and this is basically depicting the relationship between the n and the number of earthquakes m. N and m is the minimum magnitude earthquake above that they are drawing it here, and on the y-axis you have the number of earthquakes per year, and you can see this relationship is quite linear. This relation also applies in individual seismic areas with b generally about 1. The number of earthquakes depends on how seismically active an area is. The relative frequency for m is greater than 6 earthquakes, about 10 times more common than the magnitude 7, and still applies. Instead of using it for a larger area, you can also apply this relationship for a smaller area as well. There also the b value will be around 1 as well, and also you can see that if you compare the number of earthquakes happening in that region for let's suppose 6 magnitude earthquake, then the number of earthquakes for the 7 magnitude in that smaller region will be more around 10 times common than the 6 magnitude earthquakes. If you take a larger area for a larger period of time, then this relationship will hold even more true than the one that is taken for the smaller region. So, for example, in the past 1300 years, in Japan is estimated to have had about 190 earthquakes with magnitude greater than 7 and 20 with magnitude greater than 8. So you can see they are taking a larger amount of time or more extended period of time, and then they are comparing to see whether the relationship is holding true or not. You can see this is approximately holding true. So the number of earthquakes 190 is happening for magnitude greater than 7, and number of earthquakes more than 8 are happening 20. Similarly, since 1816, Southern California has had about 180 earthquakes with magnitude greater than 6 and 24 earthquakes with magnitude greater than 7 and one only for magnitude greater than 8. The New Madrid, Central USA seismic zone has had about 16 earthquakes with magnitude greater than 5 and 2 with magnitude greater than 6. Such a pattern where you are seeing the number of earthquakes are basically related by a factor, and this particular pattern is known as the fractal scaling, or you may say self similarity of, or the scale invariance, or in nature if you will find such a pattern such as the coastline or the river drainage pattern looks similar when viewed at a scale of 1, 10 and 100 or 1000. And even if you look at the snowflakes that happens, then if you look at the structure from the top and then keep on zooming it in, then you will find that the pattern is being repeated within itself. So that kind of self similarity is known as fractal scaling or the scale invariance. And this fractal scaling scenario is being also used to try to predict an earthquake by taking the dimension correlation values. Wherever that dimension correlation values drops, then it is considered to be a time that after which there might be a possibility of higher magnitude earthquake happen. So that technique is not kind of concrete. You cannot always put out a warning based on the dimension correlation values. It has also been seen that these values, even though are getting significantly lower, indicating a scarcity zone, but still the earthquake doesn't happen. So in that case, the several issues might occur. So this is about the fractal scaling or the self-similarity or the scale invariance. The frequency magnitude relations applies not only to the cumulative number n of the earthquakes greater than a given magnitude, but to the incremental number n in a magnitude range m to m plus dm. So far we have been seeing the number of earthquakes greater than a particular magnitude, but you can also see this relationship also hold true for the incremental number of earthquakes, that is n in a magnitude range of m plus m dm and m. So when you remove the log from this equation and take it this here, then it will become something like this: n is equal to 10 to the power a1 minus bm. And then if you will differentiate with respect to the magnitude and then take the logarithm, then it may become something like this: log of dn by dm, and that will be written as n, that is number of earthquakes in a particular magnitude increment, that is equal to a1 minus bm. This a1 is a different constant, or you can say a new constant, and the slope stays the constant, that is b. So you can see for the incremental magnitude and for the cumulative number of events, then there also the slope will be b, but the constant a will change. The intercept, you can say, will change. So if you look at this figure, it shows this effect, and you can see the fit is better for the cumulative number of earthquakes. This is the cumulative one. Here the fit is better for the cumulative number of earthquakes, and using more earthquakes by sampling longer interval and or larger period areas, produces better fits. Conversely, the shorter the time or the smaller the area, the more the fit is degraded by the statistics of small numbers as discussed shortly. So you can see if you compare these both of these fits, you can see the fit is better in this case, and it is not that good in the case of incremental values. Smaller earthquakes sometimes get unrecorded because of the sensitivity of the instrument, or maybe we are not interested in the smaller earthquake. There are many reasons to it. So smaller earthquakes sometimes get unrecorded, so the global earthquake catalog is incomplete. So the fit deviates from the B is equal to 1 line for very small magnitude. So if you look at this curve here, uh, let me show it to you. You can see for the smaller magnitude, that means maybe this values, you can see the curve is not fitting this straight line. That means it is deviating from the slope of the straight line, that was B is equal to 1. And also for the higher magnitude also, you may see it is again deviating. So for the smaller magnitude, you can say that the smaller magnitude earthquakes are unrecorded because maybe because of the sensitivity of the network or the instrument, or we are not interested in the smaller earthquakes. So this will deviate. So magnitude of completeness, or you can say the completeness of the catalog is not there, or you can say your catalog is incomplete. So that is why at smaller values of the magnitude it may be happening, but for the larger magnitude uh, it is little puzzling. So it, or you may say because at the larger magnitude, since we are using the surface wave magnitude here, and at the larger magnitude surface wave gets saturated and it doesn't give the right value of the earthquake, well, that might be the reason it may be happening here. And so this is what it is written: the deviation for large earthquake is expected because the surface wave magnitude saturates. So to address this issue, we can use the seismic moment, which better indicate the size of large earthquake. If you remember, when we discussed about the magnitude scales in the first lecture of module 11, then we discussed that the surface wave, body wave magnitude scales may saturate. So for body wave, the saturation point may be at around 6.2. For surface wave magnitude, it may be around 8.3. So we devised a better magnitude scale, that was the moment magnitude scale, which basically relates itself to the physics of the fault and the earthquake. So, and we also noticed that the moment magnitude doesn't saturate. So in this case also, here in the frequency magnitude relation, to indicate the larger earthquakes getting fitted onto the B is equal to 1 line, we are going to use the moment magnitude or the seismic movement that releases during an earthquake. So log of n, we are going to take a1 minus b, and log of m naught by 1.5 minus 10.73. So this is the magnitude formula. So in place of ms, we are going to incorporate this formula into this Gutenberg-Richter recurrence relationship, and this will turn out to be alpha minus beta log of m naught. And when we again fit our data according to this relation, you will see the higher magnitude earthquakes are still not fitting in that way that we were expecting. It is still deviating. So that is kind of puzzling. So that is what it is written. The deviation for a small earthquake is likely in part to be due to the incomplete earthquake catalog, but is also expected from energy considerations. However, the deviations at the large movements is more puzzling since movement don't saturate. For movements above 10 to about 27 dyne centimeter, the data are more consistent with beta greater than equal to 1. Then beta is equal to 2.3, 2 by 3. In other words, there are fewer earthquakes than expected for a given movement. Now we will talk about the magnitude invariance. In this, we are going to consider a model for this phenomena based on this concept of scale invariance assumes that the probability of an earthquake of a given size on a fault is inversely proportional to the area of the faulting involved. So the number of earthquakes with fault area greater than S should obey frequency area relation. So we are going to talk about the frequency and the area of the earthquakes relation, fault area relation. Like those, it is similar to the magnitude and the moment relation, and in this case it will become like this: log of n C minus log of S. And for constant stress drop, the moment is proportional to S to the power 3 by 2, or the fault dimension L cube. So we expect log of n is equal to C minus 2 by 3 log of m naught. And then, however, we have seen that for large transform fault earthquakes which occur on vertical fault, the width stays narrow. For example, you can see that there is this San Francisco earthquake which is a transform plate boundary. So width is narrow. Even the fault length increases. So fault length in this case is higher, or it is more. As a result, the seismic moment for such earthquake is no longer proportional to L cube and is smaller than for other earthquakes of comparable fault length. And if both the fault slip and the fault with no longer increase with length, then the fault area, movement, and the number of earthquakes should be proportional to L. The frequency, movement data give insight into the earthquake energy release because the radiated energy is proportional to the seismic movement. So here in this figure, relationship between the seismic movement and the fault length for different earthquake types is given. So here you have a length of the earthquake, and here you have the movement, and this is given. Circle is for the interplate and the square is for Japan intraplate, and triangle is the western USA, and strike slip is for the square that is filled black color. And you can see they are following a certain pattern, like this. The best fitting line is there, and this relationship is basically for the seismic movement and the fault length. The few largest earthquakes release more energy than the many smaller earthquakes. As I stated at the very beginning of this lecture, the energy released by larger earthquakes are much more than the many smaller earthquakes. So if you look at this graph, this basically gives the cumulative movement or the energy, you may say. And if you consider the magnitude of the earthquake less than 6.5 and their movement released, then it follows this particular pattern. And if you consider the earthquakes less than 7.1, that means you are incorporating larger earthquakes now, then it will having the more effect and it will show the larger moment release. As you increase the magnitude further and include more larger event, then it will become something like this. So for all earthquake, you can see there is a very large value of the earthquake. So it says that the movement contribution by the larger earthquakes itself is very large or more than many smaller earthquakes. In fact, the largest earthquake in a given year often releases more energy than the rest of the year's earthquake. So what you can see here in this table also, you can see the earthquakes greater than 8, between 7 to 7.9, 6 to 6.9, 5 to 5.9, 4 to 4.9, 3 to 3.9. The number per year, this is more than 8 is around 1, and between 7 to 7.9 is 12, 6 to 6.9 is around 110, and likewise you have these numbers here, and the energy released, that is of the order of 10 to the power 15 joule per year. So 8 magnitude, more than 8 earthquake, that is only around 0 to 1, is releasing around 1000 into 10 to the power 15 joule per year, and the rest of the earthquakes are not even close to that. You can see these 12 earthquakes together are releasing 100 into 10 to the power 15, and 110, the number of earthquakes between 6 to 6.9 is releasing 30. Even if you sum them up together also, that also will not be comparable to more than 8 magnitude earthquake. So you can see the larger earthquakes are releasing more energy, much more energy than the many smaller earthquakes here. And this figure indicates the magnitude of the earthquakes and the energy released by those earthquakes and are being compared with some artificial phenomena and as well as the natural phenomena. And you can see on the y-axis here on the left side, the magnitude are given 2, 3, 4, 5 likewise. So here some properties are also written, their classification is also given there. So the magnitude in between 3 to 5 is known as minor earthquake that can be felt by humans. Between 4 to 5 is small earthquake and it may have some property damage. 5 to 6 moderate earthquake, it may also occur some property damage. 6 to 7 strong earthquake, large economic impact may happen, loss of life also may happen. 7 to 8 major earthquake, severe economic impact, large loss of life. 9 to 8 near total destruction, massive loss of life. So, some examples are also given. So you can see the moderate size earthquake was the Duval earthquake that happened in 1996. A strong earthquake like Seattle fault of AD 900 or Tacoma 1965 earthquake. And major earthquake San Francisco 1906 or Nisqually 2001 and 8 to 9 Tohoku Japan and 9 to 10 was Cascadia subduction zone 1700 or the Chile 1960 earthquake. So if you compare these earthquakes and their relative numbers, then the magnitude between 9 to 10 is around 1 and 8 to 9 is around 2. 57 to 8 is 15 and there is 134 for 6 to 5 and 1320 is for 4 to 5. So you can see there is nearly a linear relationship, or you can say there is a tenfold increase in the number of earthquakes as you increase the magnitude by even 1 unit. And if you compare these earthquakes that are given here, then they are compared with some big phenomena that are well known. So you can see the 3 to 5 magnitude earthquake here can be compared with large lightning bolt or Oklahoma City bombing. 4 to 5 magnitude earthquake is like average tornado. 5 to 6 is like power the entire US for one day. And 6 to 7 Hiroshima atomic bomb. And 7 magnitude 1 day of an average hurricane, or maybe it may be compared with Mount St. Helens eruption. 8 to 9 large nuclear bomb test, and 9 to 10 750 days of a hurricane or power the entire US for 2000 years. So you can understand for 2000 years you don't have to produce the power, it may automatically be energized by the energy produced by 9 to 10 magnitude earthquake. And these are the energy released written over here for those particular earthquakes magnitude. So this is the summary of today's lecture. So frequency magnitude relation that we studied about, that is log of n is equal to a1 plus bm. N is the number of earthquakes with magnitude greater than or equal to m occurring in a given time. The data deviate from B is equal to 1 line for very small magnitude because the global earthquake catalog is incomplete with many earthquakes that are smaller not detected. Modified frequency magnitude relation in terms of moment magnitude can be given something like that alpha minus beta log of m naught with slope beta is equal to 2 by 3. For movements above 10 to about 27 9 centimeter, the data are more consistent with beta greater than equal to 1 than beta is equal to 2 by 3. Number of earthquakes with fault area greater than S should obey a frequency area relation like those for magnitude or movement, that is log of n is equal to c minus log of s. S is the area. These are the references, and now we will meet for lecture 5 of module 11. Thank you so much. Bye bye.